Good morning, year 13s. I've got my headphones in today because I've hooked up my headphones to my microphone because I'm going to try and use my good microphone to be able to, because obviously the sound's better, but then I'm having a couple of issues with static. So I've hooked up my headphones to it just to see whether or not I can then pick up if it goes static. Hopefully it won't. I'm just going to swing that over onto my other screen. So I've hooked up my headphones to it just to see whether quality seems to be pretty decent at the minute. So let's now pop out the chat. And then I will close. It's going to be interesting this because I'm not entirely sure whether or not it's going to make. I don't think I'm going to hear the static. I think you guys will and I won't. But we'll give it a go. We'll give it a go. Okay, let's close that down. There you go. Chat's there. If I can have Winkit. Hey Winkit. He's there. Amazing. Right, so I will first of all switch my camera to my clip cam. There we go. Sup. And then I'll leave that like that and then share my screen. Cool. So we're on the very last lesson of benzene now, folks. There we go. I think we're all up and running now. Tanzi is in the house. Sup. Sup. What's up? Cool. Okay. Last lesson of benzene today, and then we're done. So I'm going to switch my laptop over to. There we go. Right. So benzene lesson 5, last lesson of benzene before we're done. Guys, if you can just, now that I've switched to tablet mode, just let me know if there's any issues with the sound or anything. That would be grand. Okay, so last lesson of benzene today. So it's only a 5-lesson sequence. It's relatively short. Last lesson we covered, if I just quickly bring up last lesson. Last lesson we looked at the reactions of benzene. We looked at Friedel-Crafts acylation, Friedel-Crafts alkylation. Then we did nitration and halogenation. And we talked about the fact that it does its very own mechanism. So just to put like a summary of mechanisms up to where we're at. So, and this is probably worthwhile mentioning at this stage. So A-level organic mechanisms, A-level organic mechs. This is just a nice thing just to give you kind of an overview. At AS level, you pick up 4 mechanisms. You pick up free radical substitution, FRS, free rad sub. Just point out you can't write that down on your exam, either FOS or you have to write free radical substitution, you have to write it in its entirety. Then we're followed by NS. Now I'm actually doing this in order of synthesis as well. So if you ever talk, synthesis is what you get to at the very end of organics when you're starting to make molecules through these processes all joined up. So the example being, you'll start off with methane and you want to make something like 2-hydroxy 1-amino ethane or something. And then they'll say, how would you get there? And you have these multiple processes. So free rad sub followed by NS, which is nuke sub, of course, nucleophilic substitution, and then you have EA Sports. It's the game. This is electrophilic addition, electrophilic addition. So we pick up that one. That one is only done by alkenes. This is alkenes in. Yeah, so if you have an alkene on the left-hand side of any organic mechanism, then it's going to be EA. And then we have elimination. And this is alkenes out, by the way. So this is elimination. Spell that one, addition. There we go. And then we have elimination. And this is alkenes out. It's kind of how you go about recognizing these. Alkenes out, they're on the right-hand side of the equation. So those are your AS ones that you cover. And then you pick up the A2 mechanisms. And the great thing is there's only 3 more to go. So the one we've just picked up is ES. So this is electrophilic sub. This is electro sub. And this is benzene only. Yeah, the only thing that does this is benzene. So nice, easy way of being able to identify electrophilic substitution. If you're doing something to a benzene ring, sounds rude, doesn't it? If you're doing something to a benzene ring, then you are going to be doing ES. They do try to trick you by giving you molecules that include a benzene ring, and then the reaction doesn't actually change the benzene ring, and people see benzene and go, oh, it's electrophilic, but it's not. Just to show you an example of that, you know, if you have something like this, so I can ask on the chat, please, can you guys name this one, please, for me on the chat? And I'm now going to do this with HCl. HCl is a polar molecule due to a difference in electronegativity. Double bond reaches out, single bond breaks. Next step in the process, right? You're going to form a secondary carbocation. There's the benzene ring still attached. Going to form a secondary carbocation since it's more stable than the primary. Let's go the major pathway for this. And then we're going to have the Cl minus hop on now. So you phenol, yeah, be careful, Tenzi. Not phenol ethene, phenyl. Both Tenzi and Julian made that mistake. Do be careful. Yeah, phenyl ethene. Phenyl ethene. It also has a common name, which you guys have to know. I wonder if Winkit can remember what the common name is for that guy. Phenyl ethene. Thank you, Winkit. He's got the actual name. That's True IUPAC. But it does have a common name as well, which you actually have to know. This is styrene, common name, hence from polystyrene. So the mechanism for this one, please, guys. What's the mechanism here? Styrene, well done, Winkit. Really proud, dude. Good job. What's the mechanism being shown in that particular diagram? Please note that the benzene ring is not being edited in any way, shape, or form. It just happens to be in the diagram. There's nothing special about this. This is an AS mech. Just to now give you the other two for A2, we also then have nucleophilic addition elimination. No. Actually, you can actually do Na, Na, which is nucleophilic addition, nuke add, and then the last one being NAE, which is nuke add elim, nucleophilic addition elimination. And that brings you to the end of that. Congrats on 400 subs, Mr. Duncan. Well done, Julian. It is electrophilic addition. This is EA Sports. It's in the game. Yeah, this is electrophilic addition because it's an alkene in. In, add to enes. Yeah, the only thing I'm really messing with here is the alkene section. Thanks, Nish, for the congrats on the 400 subs. Do appreciate it. Anyway, and that is the total number of mechanisms for A-level chemistry. You don't need any more than that. There's only 7, which is really, really nice. You recognize that, you know, some of them are more tricky than others, but it's, you know, it's just, they're not that many. Students get really, really bogged down by mechanisms, and you don't need to. Once you kind of get to grips with them and you spend a bit of time with each of them in turn, it becomes a whole lot easier. Okay, so going back to our lesson today. So today's lesson is the final lesson in the benzene sequence, and what we're talking about today is activation, deactivation, knowing 2 specific examples of this being the phenol and the phenylamine, and then ortho-meta power projection. The understanding of ortho-meta power is technically not required. You're not required to ever draw this out, but you can't really teach it without it. Some teachers just give you the rules, and I don't like that. I prefer to do the understanding of it. So, okay, so what is activation and deactivation of benzene? Let's get rid of that. Okay, so subtitle, activation and deactivation. Deactivation of benzene. It's the deactivation song. It's a very famous hit in the 80s. So, okay, so we know that benzene is a very inert compound. Benzene, in general, is relatively unreactive. And this is due to its additional stability, relatively unreactive, due to it's nice to reinforce these terms that constantly come up in benzene, delocalized stability, localized stab. And we can even calculate this energy, stability. We can calculate this stability. We talked about this in previous lessons. We talked about, the single hydrogenation. To convert that to cyclohexane this hydrogenation process is minus 120 kilojoules per mole. So we know that if we had cyclohexa-1,3-triene, the Kekulé structure, and we hydrogenated it to make cyclohexane, this one has the addition of 1 hydrogen. This is the addition of 3 hydrogens. The expected enthalpy change would be minus 360 kilojoules per mole, but it's not. It's actually, and you have to know these values. I got it wrong last time. I quoted it, I think it was 220, and I seem to recall now it was 208. Is that right? Me getting numbers wrong. It's just as important for me to make sure that I'm checking these numbers like you are. Always check, reinforce good data. Benzene hydrogenation. I seem to recall it being 204. 208, sorry, there we go. It's correct. I got 208 correct, which is great. There we go. Amazing. So 208 is the actual value. So we can then calculate that the extra stability provided by the delocalization of benzene is going to be minus 360 minus brackets minus 208. Yeah, it's just the difference between the two of them. Run it through my calculator. Minus 360 minus brackets minus 208. Oh, syntax error. Great job on the calculator there, Mr. Duncan. Minus 360 minus brackets minus 208 close brackets. So the energy provided by the extra stability is minus 152 kilojoules per mole. So it's nice. And this is the energy of delocalized stability. Delocalization stability and energy of delocalization stab. So we know that benzene is generally unreactive. And this is key evidence for this is evidence includes the lack of reaction includes, make that a bit clearer, includes, and again changing my color, no reaction with bromine water, with Br2 aqueous. So the orange remains orange. Okay, so how could we react it? Now, the question is, the activation and deactivation is, how does the reactivity change when you add things to it? So what we now need to say is, so when benzene gains side, oh no, that's not, I was going to say side chains, but it's not, it needs to be less specific than that. When benzene gains additional structures, its reactivity changes. Now, let's look at some examples then. So, for example, expectation, we know that this is unreactive. This is unreactive, but what about this? Now, can I just point out that the words are unreactive, you'd never really call benzene a reactive thing, no matter really what its additions are, but what you can do is just compare the reactivity of the two different ones. So this is now toluene. Common name of this is toluene, but IUPAC name, IUPAC, I'm going to ask it on the chat, please. I'd love Nish to give me the answer. Can you do that, Nish? That'd be amazing. IUPAC name for that. The common name, it's nice to know this. The common name is toluene. Toluene. Oh, there you go. Toluene. And it's a colorless liquid. So the question is, who's more reactive? So I wonder if people would be able to have a guess at this. Now, the way that the understanding of this particular example comes from your understanding of the positive inductive effect. So understanding organic chemistry, like I mentioned at the start of the lesson, the 4 different mechanisms. The 7 different mechanisms. And in reality, when you get to degree level, the first thing they when you come into organic chemistry is they say, once you've got the basic foundation of these mechanisms, your understanding of the positive inductive effect and is going to then increase your ability to make adaptations in mechanisms massively. And positive inductive effect is something that's really poorly understood at A level. There are 2 reasons for this. One, because there are never any questions on it on the exam papers. So even if the teacher teaches it, most students will forget it in the course of their revision because the exams never seem to include it. There are small questions which involve it, but they're relatively few and far between. So it's definitely worthwhile doing a bit of revision on the positive inductive effect. So let's make some notes on that. Positive inductive effect. Okay, so the positive inductive effect is the idea that if you have, what's the best way of me doing this now? We will do, because it's all to do with reactivity, the identification of primary and secondary haloalkanes. So let's go for this guy. So chloromethane, AS, of course. And then we're going to do versus this guy. So the question now that I put to the classroom is, which of these is more reactive? Question. Which one will react more quickly? Which is, I'll just put more reactive. More reactive. Question mark. So which of those 2 is more reactive? Be interesting to see how long it takes you guys to see this. No, the delay is. The next one, whilst that one is being asked, I'll draw the next one. The next one is this. Chloromethane is more reactive. That's from Winkit. And Winkit, you're absolutely right. It is. Well done. So the answer to that is chloromethane. Now, they're very similar in reactivity. These are, you'd be hard pressed to be able to tell these 2 apart. You see, Julian has said the opposite. And that's the thing that we really need to clarify. So the question is, why is chloromethane more reactive? The reason being is we're now going to label the polarities. We realize that this is the first step in any mechanism. Find the polarity. Yeah? And what you realize is in chloromethane, the 2 polarities are exactly opposite each other. Yeah? The size of the positive delta is the exact opposite size of the negative delta. Yeah? That's because in this bond, the electrons are being drawn down closer to the chlorine. So that polarity is going to be between those 2. And they're going to be the opposite for this. However, these 2 are not going to be the same. So this one is going to be that, and this one is now going to be slightly smaller. It's reduced. And the reason why is that okay now, Winkit? RIP. It's really interesting. I heard the change, but I didn't hear the static, but I heard the change. It suddenly got louder in my ears. It seems to be back to normal again, but it'll be interesting to see if you guys can tell me if this is working properly. Audio. It switched over to my other one. How's that? Is that any better? Should be okay now. I'll keep an eye on it. I did hear a changeover. It suddenly went, it got louder for me. Okay, so what's happening here is the positive inductive effect. Let's actually make a note on what this is. The positive, yep, it's better. The positive inductive effect. The positive inductive effect is when a neighboring, can't spell neighboring. Is it I before E, or is it the way around? Is it? That looks better to me. When a neighboring carbon atom allows drift of the electrons in the carbon-carbon bond towards the delta positive carbon, reducing its polarity. Now that is a horrible set of words, isn't it? I mean, yuck. That is grim, that. I look at that and I'm like, oh, I don't like it. I don't have those words in my head. What I have in my head is this picture, is that I have no carbons at all. I can see the polarity. This is the picture I have in my head. Sorry, it's negative. Yeah, this is the picture I have in my head. This is it. This is all I have, a series of images. The delta negative remains the same. But now, if we have another carbon attached, it will allow drift of these electrons. Just slightly, not by a huge amount, but just by a little bit. And what impact this has is that the delta positive will be reduced. Now, these two are still classed as primary. Both of these are primary haloalkanes. Primary haloalkanes. So the difference here is negligible. But then as soon as you add another one, things change and the reactivity really does differ. Yeah, if I now have two carbons on it, the difference now becomes far more noticeable. The reactivity suddenly drops off. Yeah, this is now a secondary. This is why we categorize these, because it's far more stable and it will go through a different mechanism. Secondary haloalkane. So it's nice to remind ourselves of the AS organics. So in terms of nucleophilic substitution, we pick up SN1 and SN2 at A2 level. This is what we've now picked up. And SN2 and SN1, so which ones are they going to be doing? So before I do that, I'm just going to add on my tertiary, my final one. Yeah, and you can see what's happening here. The delta positive is being reduced. The chlorine is remaining exactly the same. The delta here has remained consistently the same size because the electrons in these bonds are still way towards the chlorine. They haven't really moved at all. But the delta positive on the carbon has now been massively reduced. Yeah, and you can suddenly see that this is going to impact the reaction that it's following. So what that means is for primaries, for both the primaries, the mechanism we see is this one. This is the mechanism we see for the primaries. Yeah, the deltas are large. By the way, you never change the way you write them, which is really frustrating. If I now do nuc sub with hydroxide ion, yeah, so that there is the mechanism that primaries will follow. And this is SN2. Now, what that actually tells us is in terms of the rate determining step, SN2, by the way, it stands for nucleophilic substitution 2 species in the rate determining step. So that's actually what SN2 stands for, which is nuc sub 2 species in RDS, rate determining step. This is kinetics. So if we had the rate equation, rate equals K, gotta love rates in A2, yeah, we're going to have both the hydroxide ion and the haloalkane and the primary haloalkane. So 2 species. both of these affect the rate. Yeah, that's what the 2 means, both affect rate. Okay, so then what happens with secondaries? Now, secondaries now do a mixture. Secondaries now do SN1 and SN2. They actually do both. They do a mixture of the 2 of them. It's a mix. So we're going to have some molecules in the secondary are going to be going through. So if I now add 2 more carbons onto this, yeah, and then label my delta, yeah, this has been reduced in size. You're going to have some molecules going through SN2. That, by the way, the negative charge should actually, I've made a mistake in that. Oh, no, I haven't. I've done actually correct. Oh. So that some of them are going to do that, but then others are going to be going through an SN2 reaction. Sorry, SN1, apologies. An SN1 reaction where the molecule fragments first. I'll put the H on there just to make this a little bit clearer. CH3, CH3, and then a H. So this is going to go through a thermal decomposition first, followed by, which the mechanism looks like that, by the way, followed by the OH minus attack in the second step. There we go. So this here is SN1, and it's SN1, even though it's 2 steps, it's SN1 because the only thing that makes a difference, the difference in the rate determining step is the first bit, because this reaction here is super fast. This is a super fast process. They're fully charged, yeah, which means this one here is going to be the slow step. So in the mechanism, in the rate equation, we're going to get rate equals K, and we're only going to have the haloalkane concentration that matters. The OH minus now no longer appears. Yeah, that is not in RDS, so therefore it won't appear in the rate equation because that one is in the fast step in step number 2. So it doesn't appear. I actually don't even like showing it at all, even though I've put a cross through it. Anyway, and then your tertiaries only go through SN1. They only do this one. So your tertiaries, your tertiary haloalkanes, tertiary haloalkanes to SN1 only. SN1 only. Due to the fact that there just isn't a big enough polarity for the SN2 to occur. Yeah, if you actually look at this, it just isn't a big enough polarity difference. Because this is still delta minus, and this has now got a tiny little delta plus. It's being reduced by the positive inductive effect. Yeah? So what that means is the original SN2 attack, charge needs to be on the correct data. Yeah, this attack here just won't happen because there isn't any attraction there. If there's not a big enough delta positive charge, then that attack won't be able to happen. It just won't see it. So what that means is you have to wait for this molecule to go through step 1, a thermal decomposition, to form the positive carbocation. And that, of course, now means it'll then be an SN1 reaction, because once that forms, this is going to be an incredibly fast step. That there, boom, step 2 is really fast, fully charged, and this original decomposition is what's going to be going on in terms of RDS. It's going to be in the rate equation, so tell you that, okay. Okay, so now that I've explained the positive inductive effect, and it's lovely to link this to SN1 and SN2. That is great organic chemistry right there, folks. It's a beautiful set of notes. That is sexy, sexy chemistry right there. Boom! That's what I'm loving. So then what about benzene? How does this impact benzene? So going back up to here, what we realize is that benzene is, the mechanism that benzene follows is ES. So let's run back through that again. So benzene follows an electrophilic. I'm being good there. Electrophilic I'm going to zoom out. It's too big anyway, and I don't like it being on the next line. Electrophilic substitution mechanism. let's have a look at what this looks like. I'm going to put an X in here. So the key thing, of course, for benzene is that you need a powerful electrophile. Yeah, so we need a fully charged example. I'm actually going to use a real one. Let's go for NO2+. And we know that the benzene is going to do this. So the electrons have to actually leave you have to drag the electrons out of the delocalized ring. And that is difficult to do. They don't want to do this. Yeah? And that's why you need a powerful electrophile. Benzene won't do electrophilic addition. It won't do it. The reason being is it's always going to want to do you know what? It's actually an interesting question. I believe it's been asked before why it won't do, or even nucleophilic. That's actually a better question. I ought to do both of those actually because they're great exam questions and they've been done in the past. I'll come back to that in a minute. I won't forget. So this step here, the reaching out of the electrons from benzene is very, very difficult. So the question would be is in this first step, how could we change its ability to do this? So if I don't actually like having the nitro there. I prefer to do it as an X. It just makes it easier for the understanding, I think. It's distracting me. I teach the way that I think, by the way, if you're ever interested. I feel like my microphone's just got louder. Let me know if there's static. So what we now do is we need to compare this process to toluene's reactions. Now, what we realize is that there is a positive inductive effect. We have the electrons in this bond are going to, carbon always does this. Whenever a carbon is bonded to a carbon, you will get a positive inductive effect. And the electrons in that bond are going to be pushed towards the benzene. They're going to be. What this means is that due to the positive inductive effect. Oh, by the way, I like to call it positive inductive effect. I like to call it the pi effect. I just think it's really nice, that pi, positive inductive. It's nice, isn't it? Pi effect. Due to the positive inductive effect, the density of electrons in the ring is increased. So if we imagine that the density of electrons in here is, let's do this. Let's say the density is this big, like that. Well, now what we've got a push of electrons here, which is going to increase the electron density. What that means is there are more electrons in that system, which make it easier for them to reach out. The density increases, so the electrons become easier to leave the ring. This is called activation. So the density of electrons in the ring increases, so the benzene becomes more susceptible to attack from electrophiles. This is known as activation. Electrophiles, brackets, activated. Activated. It's more reactive. I like it. Activated. So what I'd like you now to do to now consider in the classroom, how could we deactivate benzene? So if you push electrons towards the ring, you activate. How could you deactivate the ring? Deactivation? Deactivate? Question mark? I wonder if anyone can get it. What would I want to attach to benzene, to deactivate it, to activate, add a group that will increase the electron density in the ring, something that will push electrons towards it, move them away. Winkit, suggest how you could do this. How could you do that, Winkit? Halogen. He's on it, eh? He's on it. Well done, Winkit. Let's add a chlorine group. So this is now chlorobenzene. And chlorobenzene is exactly the opposite. The chlorine atom, the Cl atom, is high in electronegativity. It's high in electroneg. So withdraws. I like it. Julian, well done. Something highly polarizing like fluorine. Great job. Yes. I mean, you can do fluorine, but fluorine's just, you can. Fluorobenzene, never actually seen it. So withdraws, that's one word, isn't it? Withdraws electrons from the ring. Reducing its density. Deactivating the benzene. So the benzene's density, if you were to compare the picture of the two in terms of density, what's happened here is the original density looked like this, but what's now happening is it's now been reduced because it's being drawn up into the chlorine group. And the central area, this part here, is the bit that we now suddenly realize, I didn't want to do that. This region has had electrons withdrawn. So it's going to be less able, this will be able to reach out far easier than that will. I should have done them. So this can reach out easily compared to that one, which can't. So it would now be deactivating. Okay, so now we need to look at phenylamine and phenol, two important examples. So we now need phenol versus benzene. So what would we expect? And this is why this is important to discuss, because what would we expect this to do? So there's phenol and here's benzene. Would we expect it to be activated or deactivated? Activated or deactivated? Question mark. Which one would you expect it to be? Just on the chat. Be nice to see on the chat. The next one is phenylamine. Phenylamine versus benzene. Ooh, Tenzi says activated. Interesting. Julian says activated. Why would you think that? Oxygen's highly electronegative. Should be deactivating. Winkit, well done, deactivated. Annoyingly, Tenzi and Julian are correct. And this is the oddity of these two. And you have to actually be able to describe this in your versus benzene. So all of these questions come up in exams. So it turns out that these are both activating groups. They're both activated. But the explanation is very different. Or deactivated. I'm just trying to make decent notes. And I'm going to say it is activated. Tick. But the explanation is very different. You would expect, we would have expected it to be deactivating. Yeah? These two, I'm going to tie them together. Expected to be deactivating. Deactivating, but, and there's a big but here, guys. But, yeah, there's a big but. So everyone ever noticed that the B looks like a butt sideways? Anyone notice that now? No, not just me then, just me. But it was expected to be deactivating, but in fact, it is very activated. Very activating. Not just a little bit activating. Not just a little bit, but a vast amount. You're talking a 10-fold increase in reactivity. Like, it's a huge activating group. And the reason being is, what's actually happening is, and this is where I've got to do some amazing diagrams. Yeah, so here's the benzene ring drawn kind of three-dimensionally. I can do it better than that. I can do it better than this. Come on, Mr. Duncan, do some amazing diagrams. Use your artistic skills. There we go. And then here is our OH group. Now, we know that there is a delocalized pi system above and below benzene. And this is what needs to be able to reach out in a mechanism. Now, here what we also know is that the oxygen has two lone pairs on the atom. Now, here's what happens, which is super cool, by the way. And I mean like super duper cool. What happens is that one of the lone pairs on the oxygen splits off and it becomes an sp3 hybrid instead of an an sp2 hybrid instead of an sp3. And what happens is this one here, I'll color code these. I'll color code them. This one here splits off from the group. Splits off from the group to become a vertical p orbital. And what now happens is it becomes drawn into the ring. So you actually end up with a brand new image, which is really cool. It's forms so much better. What happens is instead of having, there we go, and the ring now looks like this. I actually think it probably, does it become linear? It will actually become linear. Although it still has a bond angle, in fact. It will, even though, yeah, it will, because it's still got a lone pair there. But it will be flat in reality. But what now happens is you now have a larger delocalized ring system. What's happened is it's added its electrons to the delocalized system. And you need to be able to describe this, the bullet points. OH group on benzene, the lone pair, I should have started off with that. One of the lone pairs, one of lone pairs on oxygen atom, become incorporated into the delocalized ring system, increasing, I'm very aware that my lesson's coming to an end, increasing electron density, increasing the electron density of ring, so second, third bullet point because it's a separate mark, so more susceptible to attack from electrophiles. I'm giving you exactly what it does on the mark scheme. Activated. And the same thing, activated. So the same thing happens with the phenylamine. So same gig. So in phenylamine, the original picture looks like this. Here's the ring system. Don't like that in yellow. Here's the ring system. There's benzene. Yeah. When you add on the amine group, the amine has two H's and a lone pair of electrons on the end. And the lone pair of electrons will become, it splits off, and the whole thing becomes planar again. Whole thing now becomes planar again. The nitrogen, which was before trigonal pyramidal, now actually drops into a trigonal planar arrangement. And the lone pair splits off. Yeah, the lone pair splits off to become a p orbital, which then, of course, joins the delocalized ring system of benzene. I won't bother drawing the rest of it. There we go. It becomes incorporated. And the same bullet points apply. So lone pair on nitrogen becomes incorporated into BZ's ring, increasing its electron density. Increasing electron density. More susceptible to attack. More susceptible from attack by electrophiles. Activating. Electrophiles. Activating. Cool examples. Activating. Cool. Right. So we've seen how the activation occurs. These two are the most common ones to be asked, the phenol and the amine, because it breaks the rule of electronegativity. And then, of course, the chloro deactivation one does come up as well. So they're both long answer and multiple choice. I've realized I've done an awful lot of really, really lovely chemistry today, and I've got activation, and we've done that one. And I haven't done ortho meta power projection, so I'm going to do that next lesson. I'm going to end the lesson there. I hope that makes sense, everybody. It's tough stuff, benzene. Benzene is a really challenging topic in organic chemistry. But as I said, if you learn those stories and the diagrams, it really helps. It's the diagrams that I feed off. Everything, I don't learn a set of bullet points. That's madness. All I'm doing is learning these images that I have stuck in my brain that I can then use to build those bullet points where I know the marks come from. So I will leave you guys be. Have a great rest of your day. Next lesson, last lesson of benzene, and then we'll move on. But I'll see you guys later. Take care, guys.